Good afternoon. Thank you for staying for this last talk of the day. Please feel free to ask questions as they arise. That'll keep all of us more alert. So this research was done as part of the PhD thesis of Jason Carter. Mauro was visiting us from Brazil. He helped Jason with the project. And Jason could not be here today, so I'll try to do my very best to do justice to the research. Finally got my pointer right. So we're looking at students in the act of programming, and we'd like to know the level of the difficulty they're facing. Are they facing no difficulty, surmountable difficulty, or insurmountable difficulty? And this information is of interest to instructors and other well-wishers for various reasons. And one of them is to offer help to those who are facing difficulty, especially insurmountable difficulties. Okay. Now, if the observers are right next to the students, it's pretty easy to get a good guess about the difficulty level. But it's not always practical or possible to do so. So when there's separation between the observers and the students, what we'd like is an algorithm that automatically infers the difficulty level based on the programmer actions or possibly help requests indicating difficulty. And once we've externalized the difficulty level, we can send it to a collaboration environment that can be used to offer a remote help to the students. Okay? So that's our vision. Like the idea of such a system? Yes? No? It's hard to think about it. In the previous talk, they talked about instructors offering help in large inverted classes, and in those situations, this could be useful, but there's a lot of reasons to be skeptical. If you build it, will they use it? Do students really want incremental help? And a more general question is help good for the students? What's the correlation between help and final grade? And of course, there's a technical question, how do you detect difficulty automatically? Okay? There's also the issue of the collaboration environment. What is its nature? And that's something we've addressed in other work, so I won't cover it today. Okay? And to answer the first two questions, we need to do a field study. As part of his PhD requirement, in 2011, Jason had to teach CS1 to 35 students, and we used that opportunity to gather our data for the field study. So let's look at the first question. Do students want incremental help? For 2 weeks, Jason offered help to students in groups of 3 in the act of programming. Okay? And he also offered throughout the course, and in those 2 weeks, the traditional forms of help. So the question was, what fraction of the class would come to help sessions? And anybody want to guess? I'll tell you what happened in his class, but anybody want to guess what will happen in your class? No? No one would come? 100% would come? Less than 10%. Consensus, yeah? 5%. But she's being more specific here.
What are the help sessions held? Are they held in the 2 hours before it's due?
I don't remember. I mean, I don't know, actually. I don't remember. I don't know. Okay. So, okay, good. It's always good to have surprising. So 17 of the 35 students came to the help sessions. Okay. I mean, you do have labs in which such help is offered. And this shows you why those labs are important. People will come voluntarily, despite what you might think, or at least in this class. Okay, maybe he didn't teach it well. And people gave many reasons for coming to these help sessions. It was instantaneous help. It was one-on-one help. And people felt it was more private help than in crowded office hours. Okay? It's useful to build a system that offers remote help incrementally. Okay? Maybe not in your classes, but at least in this class. Okay, so the next question is help good for the students? So during these 2 weeks, Jason monitored how many times each student asked for help. And also for a longer period of 6 weeks, he determined for each student how many times they asked for help either through email or through office hours. Okay. Okay, so he did a lot of bookkeeping. And the question is, what's the relationship between the number of times a student asked for help and their grade? Should we try again? No correlation? Positive? Negative? Negative? Positive? I mean, if it's negative, why do you guys offer help? Just because you have to do it? Because it's part of your job?
Well, if it's negative, that would be because it's the students who are like the weakest students are going to help more often.
So the weaker students are coming to help more often, and the weaker students, no matter what you do, they're going to get bad grades.
Well, that would be the argument for negative.
That's not your argument. Okay. You deserve the best answer award in the best session. So here are the data, and you can't put all these points in a nice curve as you'd like to, and that's not surprising. I mean, the grade depends on many factors, and help is probably going to be only one of them. And what you can do is, for each grade level, we can define a cluster, we can define a group, and for each group, I have plotted the median amount of help the group asked for. Okay? And if you exclude the best students and the bottom students, you see there's a correlation. It's correlation, it's not causality. Better students may ask for more help, or more help may make better students. Okay? But at least the grades do not go down with help, which many of you thought. Okay? So, build an environment that promotes help, okay, and motivates the technical research that I'm going to talk about next. So to remind you, what we'd like to know is whether the student's facing no difficulty, a surmountable difficulty, or an insurmountable difficulty, okay? And as far as we know, nobody else has tried to do this before, okay? So we don't have to be perfect, and you'll see from the results we are not, okay? But what we do is not bad for first cut research. Now, when I say that nobody else has done this before, there has been no work that has tried to classify difficulty into two levels, okay? That has tried to find these three values: no difficulty, surmountable, insurmountable. Way back in 2010, Jason developed an algorithm that did a two-way classification: difficulty or no difficulty. Okay? And this was before his class, and before he finished his class in 2011. He was able to build a collaboration environment around this algorithm, okay, which he actually used to offer help to students. And that worked pretty well. But one thing he found was that students asked for help with problems they could have solved on their own. Okay? And this experience motivated the research in difficulty classification, which was done after the class was offered. Okay? So the question for us was, how do we go from detection to classification? How do we go from a two-way classification to a three-level classification? Okay? And the first thing we tried was to come up with was using a more complicated approach, which we're calling a composed approach, because it has both a detection algorithm and a classification algorithm. If the detection algorithm says no difficulty, the composed algorithm says no difficulty. If the detection algorithm says difficulty, then the classification algorithm becomes active, and it says whether it's surmountable or insurmountable. Okay? And this algorithm doesn't care where this particular inference comes from. Okay, so it could come from help requests indicating difficulty, manually entered by the user, or it could come automatically from an algorithm. And the nature of the algorithm, its input, doesn't matter. Okay, so this is a more modular approach. Okay? That's not the reason we used this approach. We used it because it gave us better results. Okay? I'm going to focus on the classification algorithm. As you can imagine, it's a machine learning algorithm, which means we take programmer actions and convert them into features, and we use some training data to output our values. Doing machine learning, you need data. Okay, so you need input data, and in our case, that's help requests, difficulty predictions, programmer actions, and the ground truth, the difficulty level. Okay, and you need this for both evaluating and training your algorithm. We also wanted recordings of programmer screens for two reasons. First, to identify the features, and second, to determine if a difficulty was eventually surmounted or not. Okay, so that we can gather the ground truth. Okay. Now, recording field work raises all kinds of privacy issues. Okay, so we did a lab study in which we did the recordings. Okay, and this lab study, I'm sorry, I always forget that the bottom of the slide cannot be seen at the back, and just forget it each time I make a talk. So this was a 10-student lab study with advanced undergraduate and graduate students in which the screens were recorded. Okay. Here's the program they were supposed to build in about, if I can get it to, I thought I can play the video, but I guess I can't. Okay, tried it at home, it worked. So the idea was they drew a bus, both graphically and textually, and these two views were kept consistent, and the bus could be moved left or right or made into a double-decker. Okay. So after the task, Jason Carter and another coder used the recordings to do the classification, and also Jason used the recordings to find the features. Okay. When students were facing insurmountable difficulties, the time between commands increased, and programmers spent a large amount of time outside the programming environment. Okay? Now, this happens for other reasons too. If the students are idle, they'll have a similar behavior. So this was not very useful. Okay? When they were facing surmountable difficulties, there were certain sequences of actions that got repeated. And these actions are shown in this table. And you see, there's some of these actions you would expect to occur when there's difficulty. Exceptions being thrown, the debugger being used, breakpoints being set, and some actions you expect when there's progress being made, text being inserted, content assist being used. And that's intuitively right because they had difficulty and they surmounted it. So there was also progress. Okay. The last action here involves, the URL hit involves tracking the user, the browser. And all other actions can be monitored by tracking the programming environment. Okay? Each action was associated with a letter, so each action sequence was now a string. Okay? So now find those strings, those actions that represented surmountable difficulties, then we could classify all of the strings as insurmountable, because we have only two choices, surmountable or insurmountable. And now you see why the integrated approach did not work, because a non-surmountable difficulty could be either no difficulty or an insurmountable difficulty, and so we couldn't quite separate those out. Okay, so that's why the composed operation algorithm worked, because it was making fewer decisions. Okay, so now the question is, how do you match sequences? And of course, like I said, that we are using machine learning, which means we have training data that is labeled correctly. Okay, and given a test sequence, the question is how to label it. And what we did was, we found the k closest sequences in the training data to this test sequence. We found the labels of these sequences, and we reported the most frequent label in those k sequences as the action label. Okay? And so this raises three questions. How do we take a log and break it up into sequences? How do we find the distance between sequences? And what value of k do we use? Okay? So we tried two different log splitting schemes. The one that gave us better results was split by save, which makes sense because between saves you would do some logical task. Okay? And this gave us more surmountable sequences than insurmountable sequences. For similarity metric, we used an existing metric that works with sequences of different length. Okay? And to determine the value of k, 0 to 50. Okay? And we looked at the accuracy for different values of k, and there are two dimensions to the accuracy. What fraction of surmountable predictions do we get correct? And what fraction of insurmountable predictions do we get correct? Okay? And as you can see here that as k goes up, the accuracies improve, but after k is 25, saturation occurs. Okay? So that's the value we used in our final results. And you can also see that the algorithm is more biased towards surmountable. When in doubt, it says surmountable. Okay, so you get a better accuracy with surmountable difficulties. And this particular matrix here gives you the information in a more comprehensive way. This is a confusion table. It tells you for each actual label and each predicted label, P, how many values of the actual label were assigned label P. Okay? So you want a high value here and a high value here. Okay? And you can dissect this data by rows and columns. If you look at the first row, it tells you that 96% of the surmountable difficulties were correctly identified. Okay? If you look at the second row, it tells you that 63% of the insurmountable difficulties were correctly predicted. Okay? If you look at the first column, it says that when you predict surmountable, there's 86% chance you're correct. Okay? And the last column tells you that when a difficulty is labeled insurmountable, 84% chance it is correct. Okay, so what do these numbers mean? This is the metric I like best. It tells you that, so if you're an instructor, what you're going to do is look at those difficulties that are predicted to be insurmountable. Okay? And if you do so, you will look at only 29% of the total difficulties. And there'll be a 63% chance, and you'll find 63% of the genuine cases. Okay, so by looking at a small number of difficulties, we find a large number of insurmountable difficulties, okay, which is better than random at least. Okay. So what happens with the 37% in the other group? Well, the moral is that other forms of help still matter. Okay, so that's the vast majority of students were not hurt by help and probably benefited from it. Okay. About half the class wanted incremental help, okay, which was surprising to many of you. I don't know what would happen in my class also, honestly. Sequence matching could be used to detect surmountable difficulty in a composed algorithm, but not in an integrated algorithm. And by looking at a small number of difficulties, we could find a large number of the genuine cases, and traditional forms of help are still important. This is one study. Okay. And we, of course, need many more studies. And in particular, it'll be good to have, so this is one field study and one lab study. You could have other field studies and other lab studies. And in the case of lab studies, it'll be nice to have studies that don't involve the use of an API, because APIs imply web access, and web access gives you more information. So what if we didn't have those web accesses? How well would we do? I'm sure we can get better algorithms and features. And we've done a 2-level classification of difficulties, surmountable, insurmountable. You can probably have many more levels. It'll be nice to figure out a numeric difficulty, which would require a totally different algorithm. Okay? The results I show you are from an analysis we did after the fact, and we didn't actually implement code that incrementally finds the difficulties by tracking both the browsers and the programming environments. Okay? And once we build that system, it'll be nice to see how this prediction is actually used by instructors. Okay? And the last thing is what I think is the most important for scalability. It'll be nice if when I help you with an insurmountable difficulty, we record that action. So when somebody else has a similar insurmountable, the same insurmountable difficulty, we could just play back the recording. Okay? So that's something that could make this scale. Okay? Jason's thesis, and I won't go into these details here. I'll let you look at them and I'll take any questions.
So naively, and I have no idea if this is right or not, but I guess I get a similar level of accuracy by predicting that these 3 students are always facing insurmountable and these 5 students are always facing surmountable. And did you try comparing your results to any other sort of naive prediction?
Yeah. I have slides, and we have them in the paper. Okay. So the naive algorithm is random, right? If you have no information, and you look at 50% chance you'll be right. You can always predict it's insurmountable, or you can always predict it's surmountable. Okay? So you'll never detect the other case then. So as an instructor, I'll have to look at all of the cases to find the insurmountable ones if I'm always predicting one mode. We can do a data distribution also, that 71% of the difficulties were surmountable and 29 were insurmountable. So we can flip a coin that is biased towards.
That gives you some information.
So
So it's not, but you try to compare it like based on individual students or how long they've been programming, other non-meaningful information?
no, we looked at only programming actions, assumed no knowledge. This is an algorithm.
Right.
And yeah, we could try to look at what they did in the previous assignment. So like I said, new algorithms are needed. Yes.
Thank you for the talk. You reported a surprisingly high number of students wanting incremental help. How much of that do you think is due to the fact that the instructor was a junior person?
Was the junior person? Yeah, he got evaluations in like 4.9 out of 5 in the end of the course. So he did well.
No, I'm saying, like, do you think people were less reluctant to come to his asking for help because he was junior?
Oh, so they were more, I believe so. I absolutely believe that they felt more comfortable with him. And in fact, the help was offered by him and an undergraduate student. And if I was to offer help, nobody would come, I'm sure. Yes, that's a good point.
How did you categorize? Was it the students that perceived it to be insurmountable, or was it some other way of categorizing it?
Okay, so how did we decide whether some difficulty is surmountable or insurmountable? So this is a lab study. This was not a field study. So they were given like an hour and a half to do the task. We saw when the difficulty occurred. Coders looked at the recording till the end, saw whether it was surmounted or not.
Oh, okay, they
So with it, if they did it within 1.5 hours, it was surmountable, otherwise it wasn't. Again, there's many ways to probably figure that,
I was just curious.
Yeah. Okay, thank you.
Thank you very much.